Welcome back to the Deep Dive. Today we're looking at something truly spectacular, one of nature's greatest shows, the swarm. I mean, just picture it for a second. You've got maybe a million birds or a billion fish, maybe even a cloud of insects stretching for miles, and they're all moving together. It looks like one single flowing thing, perfectly in sync. The big mystery, and what our sources today really dig into, is how. How do they coordinate all that movement for safety, finding food, migrating, especially when there's no, central command, no leader calling the shots, and communication seems pretty basic. They just coordinate without crashing. It's amazing.
It really is mind-boggling, isn't it? And the science behind it, this ability to flock or swarm or school, it's still got plenty of mysteries we're trying to unravel. So to help us kind of map this out for you, we're focusing on three big questions that scientists keep asking no matter what animal group they're looking at. First, how do they actually do it? What are the mechanics, the senses involved, maybe even chemicals? Second, why? What's the payoff? What survival advantage makes all that effort worthwhile? And finally, the deeper question, how did this incredible behavior even evolve in the first place? So yeah, our mission today is to unpack the science behind it all.
Okay, let's start with maybe the coolest, most visual example, those starling murmurations in the sky. Right, you see these amazing swirling clouds, especially in winter. Flocks can average, 30,000 birds?
Easily, and sometimes much, much larger. The biggest ones recorded are estimated at over 5 million starlings.
5 million. And they're moving fast, too. Up to 55 kilometers an hour, wingtips just like 3 feet apart sometimes. It's unbelievably tight formation flying.
That speed, that closeness, it demands near-instant reactions. And figuring out the how, the actual mechanism, is a huge area of research, not just for biologists, but physicists, computer scientists.
Because it looks like a self-organizing system.
Exactly. The leading idea right now is surprisingly simple. It seems each starling basically follows one rule. Track and react to your 7 closest neighbors.
Just 7?
Just 7. They don't need to see the whole flock, don't need to know what a bird way over there is doing. If your closest 7 shift, you shift. If they slow down, you slow down.
Yeah.
And that simple local rule scales up instantly across the whole flock. That's what creates that fluid, mesmerizing coordination we see.
Wait, hold on. Only 7. Even if a hawk dives in, they're not calculating the hawk's path or reacting to the whole flock panicking?
Yeah.
Just stick to the 7.
That seems to be the key. It's the beauty of a decentralized system. That specific 7 neighbor rule, or something very like it, stabilizes everything. It stops panic waves from just ripping through the whole formation. If every bird tried to react to every other bird, it'd be chaos, total system collapse. But because they only care about their immediate vicinity, the collective reaction is incredibly fast.
Right. That makes perfect sense why people building, say, drone swarms are so interested in this.
Absolutely.
You don't want one central computer trying to micromanage thousands of drones. You want that local 7-neighbor kind of algorithm.
Yeah.
So if one drone hits turbulence, the ones right next to it react instantly.
Precisely. It's efficiency at a massive scale. But okay, if that's how they do it, the next question is why? Why fly so close together? What's the benefit?
Survival, right. That seems to be the main driver. The first idea is the dilution effect. Simple safety in numbers. If you're one starling, you're an easy target. But if you're one bird in a flock of 30,000, well, your individual odds of getting picked off plummet. It's just statistics.
It is, but it gets a bit more complex, maybe a bit darker, with the selfish herd theory. Because the dilution effect assumes everyone's equally safe, but they aren't, are they?
No, I guess not. The birds on the edge,
Yeah.
they're much more exposed.
Exactly. So while the flock provides overall safety, there's this constant internal dynamic. Every bird, especially those near the edge, is trying to push towards the safer center.
So that incredible swirling, that tightening when a predator appears, that's basically every bird for itself, trying to use its neighbors as shields.
That's the theory. It suggests the whole beautiful, coordinated dance is driven by countless acts of instantaneous self-preservation. They do fly closer together when a hawk is actually attacking, which really supports this idea.
Wow. Organized chaos driven by self-interest. Okay, let's dive underwater now. Fish school, for pretty much the same reason, safety, breeding.
Right.
But their coordination mechanism must be totally different. It's dark down there, 3-dimensional movement.
And water carries information differently than air.
You still get the survival benefits, though. That predator confusion affect thousands of shiny synchronized bodies flashing and turning. It must be almost impossible for a predator to single one out.
Overwhelms the visual system. And then there's the many eyes theory. In murky water, thousands of eyes scanning are just much better at spotting danger quickly than just one pair.
Makes sense.
Hmm.
So how do they do it? How do fish coordinate so tightly without crashing?
Well, fish have this incredible specialized sensory organ. It's called the lateral line organ. It's not about sight at all.
Lateral line. Okay.
It usually runs down the side of the fish's body, and it's incredibly sensitive to tiny changes in water pressure.
Pressure changes.
Yeah. When a fish swims, its movement creates little pressure waves, tiny disturbances in the water. The lateral line lets its neighbors feel the exact distance, speed, and direction of those pressure changes instantly.
So it's like they have built-in sonar for their immediate neighborhood. They can feel where their neighbors are without even looking.
That's a great way to put it, yes. This pressure sense lets them keep that perfect spacing and react together even when they can't see well or when things happen really fast. It's the key to avoiding collisions.
And the scale they operate on. When we think about the African sardine run,
Oh, absolutely monumental.
it rivals the big land migrations like the wildebeest just in terms of sheer biomass. These shoals, they're not just big, they're huge. Kilometers long, maybe 1.5 kilometers wide, 30 meters deep.
We're talking potentially billions of individual fish in one moving mass. It's almost incomprehensible.
And all that concentrated food inevitably attracts predators, a huge feeding frenzy.
It becomes an evolutionary arms race, doesn't it? The sardines evolve schooling, the predators evolve ways to break the school. When attacked, the sardines form these tight, spinning spheres called bait balls. Maximum density and maximum confusion.
But the predators have specialized tactics. The attacks come from everywhere.
They do. From the air, you've got gannets diving like missiles, hitting the water at 100 kilometers an hour. They have special air sacs in their head and internal nostrils so the impact doesn't, well, kill them.
Incredible adaptations. And underwater.
You see amazing strategies. Sailfish use those big sails to help herd the fish, then slash through the bait ball with their bills, stunning fish rather than spearing them.
Makes them easier to catch.
Right. Or thresher sharks, they have those incredibly long tails which they whip over their heads to slap the water surface near the bait ball. It creates a shockwave that stuns fish.
The tail slap. Wow.
And then, of course, from below, you get whales just lunging up, engulfing almost the entire bait ball in one go.
Yeah.
Pure efficiency.
It really shows that no matter how good your group coordination is, evolution finds a way to counter it. Okay, let's shift one last time from fish and birds to insects.
Right, insect swarms. Sometimes coordination involves pheromones, like with ants or bees, but movement and navigation are still huge factors.
Like the monarch butterfly migration. That's another mind blower. Up to 1 billion butterflies flying all the way from Canada down to specific forests in Mexico.
And navigating using just the sun's position and some kind of internal clock, it's phenomenal navigation.
What's really wild is that the whole round trip takes 4 generations. But the flight south, the critical one, is made by a single generation that's never made the trip before. They just know the way.
They do. Interestingly, though, sources suggest monarch groups aren't as tightly coordinated as, say, starlings. It's more like individuals all following the same map rather than constantly reacting to their immediate neighbors. Less selfish herd, maybe more worry about yourself getting there.
Right, but then you have locusts, and that's a totally different kind of swarm. It's not migration, it's transformation.
Yes, a dramatic, often destructive transformation. They start out as ordinary solitary grasshoppers, pretty harmless, but the trigger for swarming isn't a journey, it's overcrowding.
Too many grasshoppers in one place.
Exactly, and that overcrowding flips a chemical switch. It causes a massive surge of serotonin in their nervous system.
Serotonin, like the neurotransmitter we have.
The very same. But in locusts, this serotonin flood acts like a catalyst. It triggers a complete change in their body and behavior. They change color, often becoming darker or more brightly colored. They start reproducing faster, they eat more ravenously, their wings grow longer, better suited for flight. And crucially, their behavior shifts from solitary and shy to intensely social and constantly moving. They become gregarious.
So the serotonin literally turns a solitary grasshopper into a swarming locust.
Essentially, yes, it rewires them. And then these swarms grow into the billions, moving maybe not with precision like starlings, but chaotically in a common direction, eating basically every green plant in their path.
And this isn't just some ancient phenomenon. It's happening now and maybe getting worse.
While there's evidence suggesting climate change, particularly shifting rain patterns, might be creating more favorable conditions for locust outbreaks in certain areas.
Like that massive swarm in East Africa back in 2019.
Exactly. It caused devastating crop losses, impacting food security across huge regions into the Middle East, South Asia. Controlling it cost hundreds of millions in pesticides.
Which then harms other insects, too. A difficult cycle.
It is. It's an ancient biological process with very modern, serious consequences.
So if we kind of pull back and look at the big picture here, this complex group behavior, swarming, flocking, schooling, it seems to have evolved over and over again, independently, in totally different kinds of animals.
It has. Birds, fish, insects, even some mammals exhibit forms of it, and it's incredibly old.
How old were we talking?
Well, the oldest fossil evidence we have for this kind of coordinated group movement is amazing. It's a fossil find showing a line of ancient trilobites, Amphix prescus, moving together in single file.
Trilobites, like those ancient sea creatures.
Exactly. Over 480 million years ago, they were moving in a conga line, possibly for migration or maybe mass breeding, similar to how horseshoe crabs line up today. So this impulse has been around for a very, very long time.
It seems so deeply ingrained, like a fundamental survival strategy. Evolutionary models even suggest it wouldn't take that much pressure, like from predators, for this swarming instinct to evolve relatively quickly.
And you can even see echoes of it, perhaps, in human behavior. That instinct, when there's a perceived danger in a crowd, to kind of compress, to move towards the center, it might tap into that same ancient urge.
It really is stunning when you think about it, all this incredible coordination on such a massive scale, and it's maybe not about some grand cooperative plan.
It seems largely driven by billions of individual, instantaneous decisions, all aimed at one thing: survival.
Which leaves us with a really interesting thought for you to ponder after this deep dive. If the core driver for this amazing coordination, this beautiful natural spectacle, is ultimately the selfish herd, every individual just trying to get to the safer middle, what does that tell us about cooperation itself, even in our own systems? Does collective strength, that visible power of the group, always fundamentally hide a bedrock of self-interest? Is the most organized beauty in nature built on countless moments of, well, mutual betrayal? Something to think about.